Welcome back, everyone. We have a last minute change of the speaker. I'm very excited to introduce Basita. She's a grad student from the Mechanical Engineering Department at MT from the Dr. Antonio Bonacisis group. So Dr. Bonacisis unfortunately cannot make it this afternoon, but his graduate student will give the speech instead. So thanks for joining us, and I'll hand over to you.
Hi. I guess everyone can see my screen. Okay. So I'll get started. So hi everyone. Good afternoon. I am Basita, and I am a visiting grad student in Tonio's group at MIT, and I am originally a graduate student at RWTH Aachen in Germany and Forschungszentrum Jülich. So what I will talk about today is Bayesian inference for parameter estimation in energy devices. It's a project that I'm currently working with Tonio. And so the main motivation of this work is that in any kind of energy systems or in any other device systems, we have different kind of layers. Like for example, in solar cells, the system I am working on have this absorber layer, the whole transport layer, the electron transport layer, and the glass and the TCO. Whereas in lithium-ion battery, you have the electrolyte, then the cathode, anode, and the porous separator. And all these layers have their own material properties because they are usually made out of different materials. And the thing is that the efficiency of any device kind of depends on this material properties. This individual property collectively controls the total efficiency of a system. However, we do not actually have very good ways to oftentimes characterize these material properties. So we do not oftentimes know what defines our material. Like we know probably very vaguely, okay, this material does not have a very high mobility or a high conductivity, but we do not know for sure what those values are. And to increase or to improve the performance of our devices, we kind of need to know this, because until and unless we know what is the material property of a particular layer, we don't know which is the layer that is limiting the efficiency of our device or performance of our device. So from that motivation that, okay, we need to do a root cause analysis of what exactly is happening in our device, in the sense that which of these layers have a bad material property that is limiting our device performance. And we want to know further about that. So I'll tell you why this is such a huge difficulty of estimating the material parameters. For example, over here, I show you 4 current voltage curves. Okay, like normally you vary the voltage, you get a current value. And this data is from a solar cell, a perovskite solar cell that I work on. And if you see carefully, these 4 curves look very identical to each other. They have very minute differences, which are not even oftentimes very obvious to humans. But if you then look into the boxes of parameters that I have put in, I have actually varied 4 different parameters in this by oftentimes an order of magnitude. And yet by the combination of, like, I haven't varied only one parameter, I've continuously varied 4 parameters. So for different combinations of those 4 parameters, I get almost identical current voltage curves. And if we want to figure out, like we have gotten a particular current voltage curve from a device, here solar cells, and we want to say, okay, I want to fit this data to a model. It might be a simple equation you have, or maybe a more complicated device simulator that you have. You want to fit the data using your model to find out what set of parameters will give you this data. And the problem is, how do you know which parameters to choose, or which parameter is more correct? Because all these 4 curves look very identical to you. So the problem is that different combination of parameters yield very similar output, which are very similar to humans, but might not be similar to an advanced algorithm. And because of the similarity in the outputs, it is very difficult to identify what is the ground truth, what is the actual parameter set that clearly defines my experimental data. And so this is the challenge we are trying to solve. So to solve this challenge, what we need is an advanced algorithm or method which can calculate. So suppose we had those 4 parameters. What this algorithm should be able to do is calculate the property, the JV curve for different material compositions, for different parameter composition, and then able to compare that data with the actual ground truth, which is our experimental data, and then be able to give us a probability, like how closely that this data, the one we just calculated using our forward model or device simulator or a simple equation, how close is this synthetic data with the actual experimental data we have? So that is the probability that we will obtain. And it should be able to keep track of all the probabilities that it calculates at for different combinations of material parameters. So that what it will do after it has scanned the entire material space or entire parameter space, it will be able to give us a curve like this, like, along the diagonal, this curves like this, which will show, okay, for this particular combination or this particular value of material parameter, I think the synthetic data and the experimental data matches the most. So I think that here is where my device parameter is. So what in the end, what we will obtain is that we will find that this, it will give us the likelihoods of each of those variable or hidden variable. By hidden variable, I mean the material parameters, which are kind of hidden in the sense that you cannot directly measure it oftentimes using experiment or characterization methods. But it will also give the interdependencies between these different variables. So for example, if you look at this third plot along the diagonal and the fourth plot, you don't see that we get a sharp peak at one point. What we get is a distribution of probabilities. And why this is so? Because this is oftentimes what will happen, that 2 of your parameters kind of vary together. That if one varies, the other one will also vary. And what it would mean that from at least this experiment, we cannot clearly identify that particular parameter, but what we do get is the dependency of one on the other, which is actually something very unique to Bayesian inference systems that we do not see in other kind of data fitting or data inferencing techniques. So that is a kind of a solution we need. And for doing that, what we use is Bayesian inference. So what does Bayesian inference systems do? The first step is that we collect some experimental data. You ran an experiment and you collected some experimental data. Then you select a model, a forward model, or a numerical device simulator, as you might call it, or a set of equations that you think describes your system. So for example, you had a current voltage curve. Oftentimes what we do, we fit a diode equation to our current voltage curve. So it can be the diode equation that you are trying to fit with your data. And the diode equation might have some resistances, some ideality factors, and so on. And those are the parameters you are trying to extract. So you need to select a model such that you can model your experiment with that. And it will have some parameters which you want to find out. Then run the Bayesian inference plus this forward model together, because it works in a loop. So the Bayesian inferencing system would use the forward model for particular combinations of parameters and would run it, get the synthetic data, compare it with the experimental data, and tell you what its inferences are. And then for every combination of material parameters, the likelihood is calculated and the posterior is updated. So that's what I just said, that for every combination of material parameters, the forward model would be run, a synthetic data would be generated. The Bayesian inference then would compare this data with the experimental data and will give like, okay, no, the combination of parameters is bad. It does not fit our experimental data at all. So it would have a lower posterior. Whereas so another particular set of parameters, okay, this looks like a very good fit to our experimental data. So it has a higher likelihood of being true. And then when we find that, we are not really getting very close, or suppose sometimes when you have too many parameters to identify, you would find that one type of experiment is not enough, because that kind of experimental data can probably be fit by multiple combinations of parameters or multiple different combinations of parameters. So you want to run orthogonal sets of experiments that will fit the data, or that will infer the data better. So it's like kind of solving simultaneous equation, that if you have too many variables, you cannot just use one single equation to know those parameters, but you need to solve like two different equations. Okay, so at the core of Bayesian inference is this Bayes theorem. And in a Bayes theorem, this is a Bayes theorem, this is a statistical concept, and I will try to explain the different parts of it. So this is what we calculate, the posterior distribution or extracted parameters. So it's a conditional probability that kind of tells you, given our model data, the model data or the hypothesis, we call it, is the theta value or the theta. Given our model data, what is the probability that our J, that is experimental data, is true? This is the prior distribution, which is like, what do we know about our theta value? Theta is like the combination of material parameters that we think is true. So what do we know? Do we know anything about it? If we don't know, then we usually consider an uniform prior, that okay, we think all the theta values are kind of equally probable. Then this is the likelihood of the error function, that given our J value, which is the experimental data, that this is our experimental data and this is our synthetic data, what is the error between them? So that's the error function. And this is a normalizing constant to normalize the probability to 1. These are the different parts of Bayes theorem. And what we do, we give is usually when we solve the problem, we give this a uniform prior, that all our combinations of parameters are equally probable because we do not have any prior knowledge. And then we calculate this likelihood function. And from there, we update the probability posterior distribution on every cycle it runs. And we get the convergence of probabilities in certain range of parameters. So this method is actually good for certain conditions or certain specific problems. So parameter extraction from complex numerical models. So for example, you have coupled differential equations like continuity equation, drift diffusion equation. I mean, these equations are kind of common to all electrical devices, because and if you have like a couple set of equations that you want to solve, not solve, but you have a way to solve them, but you want to infer parameters using that model from your experimental data, then it is very good for those kind of systems. It is also good for inferring relations between experimental conditions and observables. Like, for example, you have you want to link your experimental conditions to material parameters, because there are certain experimental conditions you are putting in or you are varying, and then you are getting some material parameters out. This is also good for such problems. And then it is also good for identifying what is limiting your device performance. And this is the part I use it for, that I have some solar cell data and I did not know what is limiting the efficiency of my solar cells. And so I use Bayesian inference to find out which layer of my solar cell device is limiting my device. Now, there are different ways of doing Bayesian inference. I will quickly sum up 2 or 3 of the workflows. So one is this brute force method. In brute force method, suppose you want to infer 2 parameters, parameter A and parameter B. So what you do, you know the upper bounds and lower bounds, which is like the range of parameter A and parameter B. what you did would do over here, you would actually like, form like or divide parameter A and B in a uniform grid, and then run your model, which is the forward model or the device simulator you have or the set of equations you have at each of those points, and calculate all the probabilities from it. And then you will get the uniform or whatever the distribution is, like, okay, for this combination of parameter A and B, I have the best solution. For this value of parameter A and B, I do not have a good solution. And so you will get your probability distribution. The other method is called the grid search method. In this, it's kind of a little bit advanced method than the brute force method. In here, we also do a grid search, but it's an adaptive grid search. Instead of uniformly dividing parameter A and B, the parameter space, finally, from the very beginning, what we do, we start with the coarse sampling method, as shown in this picture over here. And then as we go on improving or go on finding that, okay, for this kind or this set of parameter A and B, we have a higher value. Okay, then we will sample more in this region and not sample elsewhere. And that's why you see in this figure, what I show is that as you progress from one iteration to another, your sample space actually decreases, or your sampling resolution increases, and you converge upon this high probability regions. There is another method which is like the advanced method or the most cutting edge that we are using now. It's called the surrogate model plus MCMC. So what happens is that in this case, you replace your device model or your equations with a neural network or a deep neural network to represent your model. So what happens, why we do this is that oftentimes when your model is a device simulator, you actually are like, kind of limited by the speed of this device simulator. Like in my case, my device simulator never runs in parallel. It can only run once, one at a time. And so what happens is that for this MCMC is a sampling process, and this is an automatic sampling process. For this to work, we need a lot of calculation. We need to calculate our model at a lot of different points. And this process will be very slow if we were using by default only this original model. So what we do, we create a training data set, and with that we train this neural network model or deep neural network model as to act as our surrogate model, so that the surrogate model can then replace our forward model. And what happens is that you achieve like orders of magnitude of fast. You make the whole process fast, because the surrogate model can run in parallel, and it can run much faster, like at least 2 to 3 orders of magnitude faster than the actual model usually. So we use the surrogate model instead of our original numerical model. And then what we do is that instead of dividing this space manually, like in the brute force method, like fine sampling from the beginning, or in grid search, successive sampling on every iteration, we do not control this grid search anymore. What we do, we use this thing called Markov chain Monte Carlo. And Markov chain Monte Carlo is like a random sampling technique, but what it does is that we call them walkers. So for example, you have this space, or you have a space where somewhere probabilities would be high, somewhere it would be low. What Markov chain Monte Carlo would do for you is that it will set like walkers. We call walkers, you can call them samplers. It will have a certain set of samplers. It can be like, I usually increase the samplers, like use 512 or 512 to 256 samplers. And what they would do, they would scan this whole space. So the walkers would go into this material space, and they would sample at random points and find out what the probabilities are. And like in these two graphs, these are called mixing plots. So what mixing plots would then tell you is that each color in like, I mean, you cannot see anything clearly in a mixing plot. And that's the whole point, that it shows that the walkers are actually, or the samplers are actually scanning this entire space, but then they are converging on the most likely range of your parameter. So here for parameter A and parameter B, my walkers, which were like, I think 128 to 256 walkers for each parameter, they sampled this entire range of parameter A and parameter B that I have set, and they figured out that no, in this range, it is most likely that parameter A is or parameter B is. So to sum up, in the first two methods of brute force or grid search, you are always limited by the speed of the model or the speed of your device simulator. Also, you are limited by the user-defined grid resolution. At least in the first case, what happens, whatever your grid resolution is, you cannot zoom in further than that. And also, the grid search method is like this method, the second method, is not good if your parameter landscape is not uniform. Why? Because, for example, say while we were doing this, it saw that parameter A has a high value here and parameter AB has a low probability here. But what if we did not have a smooth transition from high probability to low probability? What if our landscape was ununiform and we were seeing certain increase in probability and it was like low probable region on either side of that? Like, for example, in the middle or at the center, it is very likely that parameter A and B is somewhere here, but we sampled somewhere else, so we'll never find that one. Whereas in case of MCMC or Markov chain Monte Carlo, we do not need to define any grid size. It's completely upon the walkers, and it's a random statistical process that it will crawl the whole space and it will find out how the landscape looks like for the parameters. So yeah, we have published quite a few results using all these methodologies, and I will walk you through a little bit of what we have achieved so far. So this was like the first iteration of Bayesian inference that we did in this lab, and we were trying to figure out the parameters from a tin sulfide solar cell. And there are a few things that we learned over here in this work. What we did is, first of all, we plotted the entropy. So what we did in this plot is that we wanted to see how the probability or how the posterior distribution of our parameters kind of converges as we go on increasing the amount of data. And what you will see, like, this is the entropy of these 4 variables that we have plotted here. And you see that as we go on increasing the amount of data, or amount of experimental data to be specific, the algorithm sees the probability converges more and more, and we see a decrease in entropy. However, sometimes we also see an increase in entropy with data, and this is probably due to the noise that is present in data. Also, we saw that some parameters cannot be resolved uniquely, and like I described earlier, but we see a correlation between 2 parameters. Like, this is the correlation here between this and this parameter, and so even if the mobility and the lifetime does not converge on their own, we see that their product actually is kind of convergent. In our next iteration of the problem, we built an entire an open source software to do Bayesian inferencing using adaptive grid search method. And here we used our previous data, like the data from the posterior distribution from this work as our prior. So we did not use an uniform prior in this case, and we wanted to improve on that system. And what we saw is that, especially in the case of the lifetime, our probability kind of converged more. Whereas in this case, we saw that we find a different higher probability region from the one, it is very adjacent, but we found a different high probability region in this case than what we did using the brute force method. Finally, we also used the surrogate model plus Markov chain Monte Carlo technique, But this we used for actually something a little bit different, which was it was used for a Bayesian optimization problem, and we were trying to optimize the performance of gallium arsenide solar cells. So what we did in this case, we took some process parameters. So usually in any kind of optimization problem, what happens is that, okay, I vary the process parameters and I get a device performance, and you try to draw a direct correlation between these two without having to actually understand what is going on in the middle, like what is changing if I change my process parameters that is actually improving my device performance. So in this case, what we did, we actually calculated the material parameters using some Arrhenius relationship between the process parameters and the material parameters. And in this case, we actually use the surrogate model to train our neural network to act as our forward model or the device model. And we saw that, and we actually improved the device performance by optimizing for the growth temperature of the different layers using this method. Now, in my project, what I did is I was building on top of this work, and I was using my the Bayesian inference system using surrogate modeling and Markov chain Monte Carlo for the purpose of improving a perovskite solar cell. So in my system, what happens, there are like mainly 3 or 5 layers. So I have the absorber layer of perovskite, I have the whole transport layer, electron transport layer, which actually extracts the electrons from the device, the electrons that are photo-generated. And then there are interface. The interface properties are crucial. So what I did is that there are like lots of parameters that I need to adjust to actually figure out what is happening in my solar cell. And roughly there would be like 20 unknown parameters, combining all these layers. And it's not a very easy task to do it. So we need to kind of select our model carefully. We need to figure out if we need more than one equation or one kind of experiment to do this, because we are doing it for so many parameters. Yeah. So that's my problem. And what I have learned from doing these methods or working on this problem is that it's not so straightforward to apply just a off-the-shelf algorithm directly, or even not an off-the-shelf algorithm. Like you have done it for, say, 4 or 5 parameters, and you want to now do it for 11 or 12 parameters. It gets pretty challenging. So what a few things that I have learned is that, like, the region from where your walkers or from where you were starting to sample, it kind of matters. Like these are 2 identical, these are, by the way, corner plots. So in where what I plot along the diagonal are the posterior probability densities of my parameters. I think this was a 10 or 11 parameter system that I was dealing with. And in the inside, what I have are the codependencies of the various parameter combination. And these are 2 identical data sets, but you see that the distribution I get from these 2 are different. And here especially, you see that there are some multimodal distributions of these parameters that I'm seeing. And by multimodal distribution, what I mean that the system finds out that there could be 2 different values or 2 equally probable values of my parameter that can satisfy my system. And this can be a common problem when you have like a huge number of parameters. So what I found out that it's better to have more types of experiments that you are running your Bayesian inference system on, but it also helps if you kind of figure out what's a high probability region using another data fitting algorithm, and then start your walkers from there or start sampling from there. What it does is that it prevents your walkers to oftentimes get stuck in low probability region. So that was one learning that I had during my project. The other one was that, yeah, so this is actually the continuation from that slide. So here, the starting conditions of my walkers were different. And you see that the results it finds is also different. So most of the parameters it found the relation with temperature are identical in both cases. But the third case, for the surface recombination velocity, we see a different kind of distribution or different relation between the temperature and the surface recombination velocity, depending on where my walker started walking from. And so this is something ones need to be careful about. The other thing I found is that the surrogate model is crucial, because if your surrogate model or if your neural network training is not highly sensitive or has a low enough error, then what would happen is that the MCMC would find that, okay, maybe one of the parameters do not really matter because your neural network is not sensitive enough to identify what the change in that particular parameter is doing to your system. So that's kind of also important to keep in mind. But from all this learning, ultimately what I could do is I could actually extract like about 8 parameters from 4 current voltage measurements, illumination dependent measurement of my perovskite cell. And then I identified that which of these 3 layers or 5 layers is actually limiting my performance. So if you look into the box, what I see is that my surface recombination velocity at one of my electron transport layer, like the layer through which the electrons come out, is actually pretty high. So therefore, my electrons are recombining very fast at that interface, and that is limiting my performance. And here is actually the full plot of all the 8 parameters that I worked with. And this one was just a smaller version because, I mean, it's kind of difficult to see. So the key takeaways from my research was that it's important to have like high probability starting point for my walkers in Markov-Chain Monte Carlo. The sensitive the more forward model is, or the your deep neural network is, the better. And the training loss of your surrogate model definitely matters. Keep it as low as possible. And feature selection sometimes might help. Like when you have too many parameters and you don't know what to do, then if you do a feature importance ranking, then you might want to reduce the number of parameters which do not affect your data as much as the others do. Yeah, so that was all I had for the presentation. And now we are working for developing multi-objective Bayesian optimizations with more, in which we would be comparing more than one type of experiment at once. We want to extend this methodology to other energy systems like batteries. I'm working on a battery project currently, and or any other interesting systems. But these methods are not limited to energy devices, but it can be used for any sufficiently complex device simulator. Yeah, and we are looking for other collaboration partners who would like to use this method for their problem. Thank you.
Thank you for your talk.
Yeah, thank you.
We for a 4-minute Q&A. So any questions? Okay.
Hi, great talk. There were a lot of things very useful for the audience here. One of the things you were showing consistently was these joint plots of multiple parameters in the posterior distributions. And you told us how you got insights from the marginal distributions like the multimodal and so on. Were there interesting examples where you got insights from the shape of the joint distributions of pairs of parameters that you did not expect from your existing knowledge of the interdependencies of those parameters?
Yeah, like for example, you can still see my slides, right?
Yes.
Yeah, okay, great. Yeah, for example, in this very case, for example, here, the mobility of one layer, and this was like the valence band offset. And I mean, when we see it, it's kind of obvious that, yeah, it will happen. but we did not know this, that this interdependence would exist. So what happens is that as the mobility goes down, our valence band offset kind of increases. And this makes complete sense because when the mobility goes down, you would have less extraction of charge carriers. And then if the valence band offset also increases, then there are more charge carriers flowing out. So this is a new inference that we got that we did not know exist, but it makes complete sense.
Great answer. Thank you.
You're welcome.
Hey, Basita, you started off by talking about the goal or the challenge of improving the materials in the device to improve the overall performance. And I'm wondering if when you look holistically at everything you learn, does it suggest that we can lock in all of the other components and then really work on a specific material to make it as good as possible? Or does your results suggest if we really want to optimize the efficiency and stability of an organic photovoltaic device, we have to optimize multiple parameters in parallel because of their interdependencies?
So that's a very good question. Thank you for asking that. So, I mean, I think the answer is two-folded over here. So there are two things to learn. First of all, yeah, oftentimes you would see that you have existing material bases that you can tweak and optimize multiple layers at the same time to get a better device. That's true. But oftentimes from the insights we get that, okay, this is the particular layer that's not working. And if you have like material development capacities, then you can use that like because you know all the other parameters in your cells. So you know what kind of a material or what kind of a material parameter you need. And then you can do a material discovery to change that particular layer. So I would say that this work or Bayesian inference kind of tells you what is all wrong with your device, and then how you want to develop or how you want to improve it kind of depends on you. But you can do both from the inference you get. Does that answer your question, sir?
Yes, and I guess the implication is sometimes from a practical perspective,
Yeah.
a team will be in a position to, let's just say, work on a material.
Yeah.
It's very eye-opening from your talk to see how the complexity of the device really
Absolutely
prospectively considered when you're trying to optimize the material, because it may or may not plug back in and improve the overall device properties, depending upon how it obviously interacts with the other layers. And
yeah.
Anyway, it's very eye-opening. I appreciate the way you've kind of dissected the problem, and the answer is very helpful. Thanks.
Thank you.
Well, thank you.